Good news for students who want to build machines to enter in the robot contest, Robocon. Professor Masashi Shimizu of the Tokyo Institute of Technology has made this video to share some simple tips for building a successful machine. Nicknamed Dr. Robocon, Professor Shimizu has been chairman of the judges panel for more than a decade and has attended tournaments throughout the world. We're sure that his simple tips will prove useful.
Hi everybody, and this is Professor Shimizu. I'm working for Tokyo Institute of Technology, and for the last 10 years I was in charge of the robot contest in our university. And this video is for the beginners of robot contest. And if you want to join the robot contest, you have to make machines. And the machines for robot contest have many limitations. For example, limitations for weight, limitations for size, and the limitation for energy. So you have to make very light and strong and very low friction machines. In this video, the 5 key points for the robot contest machine will be explained.
Robo Basics. Wheels and bearings are basic elements in a Robocon machine and can be designed in many ways. Point number 1, shaft bearings. The first point is the shaft bearing, which is used in many places, like the wheels and arm. Today, we'll look at how they're used with wheels. This is a cross-section of a bearing. Here's the shaft, and here's the bearing. With bearings, it's important to reduce two things: the friction force and the torque needed to turn the shaft. As shown here, the friction force is determined by multiplying the force applied to the shaft by the friction coefficient. The torque needed to turn the shaft is found by multiplying the friction force by the shaft radius. To reduce the torque, you must reduce the diameter of the shaft, while being careful to maintain sufficient shaft strength. But how do we reduce friction force? We can either reduce the friction coefficient or the amount of force applied to the shaft. We can cut the friction coefficient using oil or grease. But how do we reduce the amount of force applied to the shaft? This is a bearing. We'll use a wheel as an example. Here's the wheel, the axis, and the bearing. This is an example of bad design. When a wheel is overhung on two bearings like this, a very large force is applied to the bearings. This is shown in the equation here. The force applied to the inner bearing, compared to that applied to the wheel, is the same as the ratio of L3 to L2. The force applied to the outer bearing compared to that of the wheel is the same as the ratio of L3 to L1. In this example, the ratio of L2 to L3 is about 2, which means that the force applied to F1 is about twice the amount that's applied to the wheel. The force at F2 is about the same as that applied to the wheel. Adding these together, the force applied to the bearings is 3 times the force that's applied to the wheel. This is the ideal design. The wheel is supported by bearings on both sides. In this design, each bearing receives half the force that is applied to the wheel. Therefore, the two bearings together receive the same force as the wheel, which is only 1/3 of the force shown in the previous example. A simple test will demonstrate what a big difference this makes. Let's see how much force is needed to move the machine when the wheels are supported on both sides. This gauge measures the amount of pulling power needed to move the wheeled platform. begins to roll at about 170 grams. Now, let's see what happens when the back wheels are supported on one side only. They begin to roll at 400 grams. As you can see, single-sided support greatly increases friction, so use double-sided support whenever possible. This test demonstrates how important it is to reduce bearing friction. When building your machine, use this ideal design if you can. If you have to use single-sided support, minimize the distance between the inner bearing and the wheel, and maximize the distance between the bearings. What should the machine's frame be made of? Point 2. Materials. The second point is about using light and strong materials to build your machine. The shape of the cross-section of the material is crucial. To demonstrate this, let's make an arm from this material and conduct a test. First, we'll hang a weight on a horizontal arm that's standing on its side. It only bends a little. If we put the weight on a horizontal arm lying flat, the arm bends much more. Even with the same material, you can see that the shape of the cross-section and the way it's used are extremely important. Let's analyze the results of this test. This graph shows what happens to the strength of a quadrilateral material when we change its shape while maintaining a constant cross-sectional area. The strength obtained with a square cross-section was assigned a value of 1. When a rectangle was used with a long side set vertically, strength against bending is increased 3 to 4 times. When the long side is set horizontally, strength declines. This shows that a vertical orientation is best. Here's some advice about machines with arms that have serious bending and strength problems. Let's go back to that bent arm. As you can see, the arm's end is almost straight, but it's very bent up here. The strength of a bent material is determined not only by the applied weight, but by the distance of the weight. Therefore, one should avoid placing weight at the end of an arm. When mounting a motor, for example, it should be mounted near the arm's fixed side, not on the end. Now, let's look at what happens with tubular material. This graph shows the results obtained with a steel bar and hollow tubes that have the same cross-sectional area and weight. The horizontal axis on the chart is the radius ratio. As the radius ratio increases, the material gets stronger against bending, even though the material's weight remains the same. So, using material shaped like this lets us build lighter, stronger machines. Now, let's compare the strengths of different materials. You might think that you should use steel because it's so much stronger than aluminum. But actually, we have to consider the strength-to-weight ratio to see what's appropriate for a Robocon machine. This table compares the strengths of different materials of the same weight. From the top, we have steel, stainless steel, brass, and aluminum. As you can see, weight for weight, aluminum is about 5 times stronger than steel. Stainless steel has about the same strength as aluminum. and brass is very weak. For Robocon machines, then, it's best to use either stainless steel or aluminum. So far, we've focused on metals, but natural materials like bamboo and wood also have excellent properties. Let's demonstrate with this bamboo pole. This pole measures 1.5 meters from red tape to red tape. If we were to make a bamboo arm of that length, could it support a 2.2 kilogram weight? Let's find out. It bends, but it still supports the weight just fine. Calculating the data from the bamboo, we find that it's stronger than a 12-millimeter aluminum rod of the same weight. I think this test demonstrates that natural materials have excellent strength. I highly recommend that you use them. Point 3. Tensile Force. The third point is using tensile force to strengthen your machine. Even if all the parts are shaped correctly and the appropriate materials are used, the lighter you make your machine, the less strength it's likely to have. One way to fix this problem is with string. String is very resistant against pulling force, which we call tensile force, but has almost no resistance against compression. Through the skillful use of these properties, we can create a structure that's both light and strong. Let's demonstrate the effects of tensile force on this wobbly frame. If we tie hemp twine tightly on the diagonals, the frame becomes rigid. It's very strong. A person can sit on it. Point 4. Mobility. The fourth point is the machine's mobility. How many motors do you think are needed for a Robocon machine? If you imagine a car, you might think that it needs only one motor, just like a car has only one engine. But cars have differential devices that permit their rear wheels to move in opposite directions. They also have steering mechanisms for their front wheels. It would be very difficult and expensive to adapt such devices to a Robocon machine. That's why two motors are often mounted, one on each drive wheel, and different running speeds are used to steer. Using this diagram, let's look at a machine with a motor on each drive wheel and consider how it turns. One wheel is moved by force U1, the other by force U2. The machine turns around this point here. As it turns, the front wheels turn in this direction. The forward component of this motion presents no problem, because the wheels turn. However, the lateral component causes slippage. Therefore, this construction results in poor mobility. That's why casters are often used in front to prevent slippage. Either that, or the wheels are replaced with runners. Although slippage still occurs with runners, the problem can be mitigated by using material with a low friction coefficient. Some people have a preconception that runners are no good because of high friction. They think that wheels must be used, but actually runners are very effective on Robocon machines. Let's try an experiment. This is the machine seen from the bottom. These are the drive wheels, and these ping pong balls are the runners. We'll put a 1.3 kilogram weight on top. Casters work smoothly when the machine is turning. But when a sudden shift is made from forward to reverse, or from reverse to forward, the casters must turn 180 degrees. This means one of two things. Either the chassis jiggles laterally, or the caster axle shifts. Either way, resistance will sometimes result. Point 5. Pulling force. The fifth point is pulling power. Strong pulling power is needed to climb inclines, move heavy objects, and push against opponents' machines. These two machines feature the same materials, the same design, and the same parts. The only difference is that this one has a four-wheel drive, and this one has a two-wheel drive. Rubber bands and pulleys were used to achieve a four-wheel drive. Pulling force is determined by the amount of friction force that's applied to the tires. It's the product of the force applied to the tires times the friction coefficient, which we assume is constant in this case. The four-wheel drive car carries all of the car's weight on its drive wheels. Therefore, the pulling force equals the weight of the car times the friction coefficient. In contrast, the two-wheel drive car carries only half of the car's weight on its drive wheels. This reduces the pulling force by half. Let's see this difference in action. Let's start with an incline. First, we'll try the two-wheel drive. It can climb a pretty steep hill, but when it gets to about this angle, it can't go any further. Now let's try the four-wheel drive. It has no trouble climbing. Even at this angle, it still goes. When we bring it up to here, it finally starts to slip. Let's see what happens when the machines push against each other. The four-wheel drive is on the left, the two-wheel drive on the right. Because the four-wheel drive has such strong pulling force, it easily pushes the two-wheel drive backwards.
And did you get these 5 key points? I really hope you can use these ideas, and that you can use your important time to realize your own ideas for your machines.
An understanding of these Robocon basics can save you valuable time when making your machine. We hope you can use them to make wonderful robots that display your creativity to everyone at the Robocon contest.
Good luck for your robot contest, and goodbye.
Goodbye.